Welcome everyone for the fractional calculus seminar series. Today we have Professor Daniel Hahn, has completed his PhD in applied mathematics and cell biology at the University of Manchester. After a postdoctoral fellowship at the University of Cambridge, he received a permanent position in the School of Mathematics and Statistics at the University of New South Wales, where he is now a senior lecturer. He works at the interface of stochastic processes, fractional calculus, and biology. We are very happy to have you here, Daniel. You may please begin your talk.
All right, thanks very much for inviting me today. So the topic of my talk is variable order fractional diffusion. And this topic has been one that I've been working in since, I guess, second year of my PhD. So as Pavan very nicely introduced, I'm from the University of New South Wales here in Sydney, Australia. So the phenomena of anomalous diffusion is really where we begin, where you have something called the mean square displacement, and that's the equation that you see here in the middle at the top. And basically what it measures is the amount of spread that a particle has. In mathematical terms, it's the second moment of your stochastic process. And usually for diffusion, you have that the second moment, the mean square displacement increases proportionally with time. So you have some diffusion coefficient, some constant coefficients multiplying t, and that's how your mean square displacement evolves. And that's the black dashed line that you see in the plot. Now, this was observed by Brown, and hence why the name Brownian motion in the 1800s of pollen molecules floating around on the surface of water. Now, as we got more and more sophisticated biological experiments where we are observing different objects, I guess, freely diffusing or subdiffusing, superdiffusing inside crowded media, inside active systems where energy is being pumped in to move objects, what scientists started to observe is that actually there's a whole class of different motion that is not Brownian, so the mean square displacement doesn't increase proportionally with time and increases either slower or faster than diffusion. And this is what you call subdiffusion for when it's slower and superdiffusion when it's faster. And so you see this kind of anomalous diffusion process like subdiffusion when you talk about molecules floating around on the surface of cells or on the surface of lipid-bound membranes, as well as in passive transport of cargo. So inside a cell, everything is subdiffusive. You also see superdiffusion of cargo transport when they're being driven by microtubules. I've not yet also come across anything that's higher, has an exponent higher than 2. So I should explain this mu is what you usually call the anomalous exponent or the fractional exponent. And mu greater than 2 would imply that something's moving faster than finite velocity process. Okay, and as you see from all the citations, anomalous diffusion is everywhere in biology, and that's really what's motivating the talk. And underlying this observation, there are actually many stochastic models that one can formulate that will give you something that looks like anomalous diffusion. On the left, you're seeing something like a continuous time random walk, usually referred to as a CTRW. And so in green, you're actually seeing something that's super diffusive. So you see these things with like very long flights with interspersed tiny little jumps. In red or magenta, you're actually seeing subdiffusion when something is trapped. And in blue, you're seeing regular diffusion, which is the motion that we would expect. This is all in 2D, of course. On the right, you're actually seeing something called fractional Brownian motion. So it's a Gaussian process just with a very funny correlation function. And you'll see also there's a h equals a half actually corresponds to Brownian motion, so mu equals 1, and the magenta h equals 0.2 corresponds to subdiffusion, and as you can see, h equals 0.8 corresponds to superdiffusion. Today I'll be mostly talking about models from the continuous time random walk perspective, but it's good to know that there are other models that generate anomalous diffusion. So the continuous time random walk can essentially be seen as a stochastic process where you have a random walker on a lattice position, and it waits there a random amount of time, capital T, before jumping to the next state. And so if I decide that actually T is going to be distributed exponentially, then what I obtain from, let's say, a nearest neighbor random walk, which is what you see in the diagram here, where particles or random walkers are actually jumping to neighboring sites separated with distance delta x, you end up with a governing equation in discrete space that looks like the one you see on the slide. If now, instead of some constant rate of jumping, you actually introduce a residence time dependence rate, which is actually a Mittag, for specific purposes here, we'll say it's a Mittag-Leffler function, but actually you can have many other residence time dependence weights that generate waiting time distributions like the Pareto or any kind of heavy tail distribution. What you end up with is first of all, when you have this kind of distribution, the Mittag-Leffler function that you see here, you usually have a divergent mean, meaning that the average time you spend at one site, it's basically undefined. It could be infinite. If you now formulate a governing equation of how your probability density function spreads on the discrete lattice, which is px plus delta x, position x plus delta x, then you end up with some equation like this. And the operator that you're seeing here, this d to the power of 1 minus mu subscript t, is what you call the Riemann-Liouville fractional derivative. And this can be derived in the following way. So you have a probability density of finding your random walk at some position x at time t. You now can describe that probability as the probability that you survived up to time t given your initial data at the position x, plus the positions that survived some smaller amount of time, t minus t prime, having arrived at that site x at t prime. And that j is exactly that arrival flux. So here j is saying what is the rate of arrival of particles to position x at time t prime. And if I now integrate all of that from 0 to t, so from the beginning of my random walk to current time, then I obtain how much probability density should be located at my position x at time t. Then next, what I'll describe is I will define is the escape rate. So this is basically saying how much probability density, or I guess within a finite interval, you can call it a probability mass, how much of that is leaving my site x or some finite intervals of space. And that's basically the same formulation, but you basically just have how much of your probability density is leaving, determined by this multiplication factor of your waiting time density, given your initial data. And you add to that basically the exact same formula, except now you've changed your survival function into a probability density. Okay, so the top is the probability density, and the bottom is the escape rate. Okay. If I now transform these into Laplace space, what I can do is I can get a nice expression of my escape rate in terms of my probability density function. And this phi is what we're going to call later our kernel, but this kernel is actually entirely determined by how I wait at certain sites. Okay. And so what I now have is the arrival rate is then, so the arrival rate j, which if I can now express that in terms of I can close my equation for p. The arrival rate is essentially however much escape happens at every other site, x minus z, and then jumps into my site x. So that's I x minus z at time t and wz. So the arrival of particles or probability density into my site x at time t is equal to the amount that escapes from every other position and then makes a corresponding jump, which is probabilistically described by wz. So that's my kind of jump probability. And what we'll say that for now is specifically we'll define that as the sum of two delta functions, which will then give me half escaping from the left and the right, both coming into x. So this is your typical unbiased random walk transition kernel. Okay. If I then take all of these elements and I substitute them into my original equation at the top, and I take the time derivative of that, I can express the evolution of my density as the amount of arrival minus the amount of escape. And that can basically just be described by this formula here. And this looks frighteningly similar to your typical diffusion equation formulation from a random walk, except now you have this phi x t minus tau, t minus t prime, which is essentially describing the amount of escape that's occurring or arrival that's occurring because of a non-constant rate, okay? And you can see this also when you take the Laplace transforms of your waiting time densities for an exponential, the kernel just becomes constant, whereas for a power law or heavy-tailed waiting time distribution, you have something that actually depends on the Laplace space variable S here. Okay. Then once you determine your kernel, so with the Mittag-Leffler function, as I said, you end up with this object called the Riemann-Liouville fractional derivative. You can then take the diffusion limit where you say that delta x squared, with delta x being your lattice size increments, goes to 0 as your time scale goes to 0, which is tau, and such that this ratio here is kept constant into an anomalous diffusion coefficient or a generalized diffusion coefficient. And what you'll end up with is you'll end up with the fractional diffusion equation. So the equation in the middle that you're seeing is what you call the fractional diffusion equation. And the object that you see inside that object that we saw before is what we call the Riemann-Liouville fractional derivative. Perfect. Everything should be very familiar so far. And here are all the definitions. So one very useful property of the Riemann-Liouville derivative is that its Laplace transform is essentially just the Laplace variable to the power of 1 minus whatever the exponent was. And all of this has been outlined quite a long time ago and there's a fantastic review by Metzler and Klafter in 2000's Physics Reports. Now what we're going to do is we're going to say, okay, what happens if my environment then becomes heterogeneous? So I know that in real life, my fractional diffusion doesn't occur in empty space where everything is homogenized. There are environments where things are more sticky than others. There are collisions that happen more often than others, more crowding, different property of the fluid itself, the space in which you're moving. And experimentally, this has been reported relatively recently. I guess it's been 8 years now, that organelles, or these objects that move around inside cells that are critical to life, they actually move in a heterogeneous matter. And so what you're seeing in this picture here, the blue is kind of like a nucleus of a cell, so it's kind of like controlling center where all the DNA is. And the green dots that you're seeing are the little lysosomes, which are the organelles that I was talking about before, that are being displayed. So these usually move around. In this picture, it's obviously frozen because it's a picture. But the question becomes, how can we model the movement of subdiffusive organelles in heterogeneous environments? Now, the even more interesting note is that we know that these organelles aren't really performing in any active motion as per se, and yet they still form these clustered distributions. And so can we also explain why something moving predominantly subdiffusively should form these stable non-uniform clusters? Because if we're not pumping energy into the system, and if things are moving slower than diffusion, we should actually see them tend towards something uniform, right, in the long time limit. So the model that we're going to consider is we're going to say let the fractional exponent vary over space. So we're going to change that mu that we saw previously and say that, well, now that parameter mu depends on space itself. And so then we obtain what we call the space-dependent variable order time fractional diffusion equation, which is a bit of a mouthful. And the Riemann-Liouville derivative here, the definition has changed slightly so that you have to include now spatial dependence in all of the exponents that occur, so inside the gamma function and inside the integral with the power law kernel. And this has also been derived and explored quite a lot. So since 2002, the canonical model came out in 2005. And then 2009, there was a study on the equation properties, analytics, and that's actually an ongoing field of research. And so I want to take you back to the derivation because I want to see if there exists a diffusion limit that satisfies, that leads us back to the space-dependent variable order time-fractional diffusion equation. I want to make sure that changing my waiting time as a function of x, such that it depends now on position, doesn't actually affect my diffusion limit. So from before, we say the waiting time density is a Mittag-Leffler function like this. And then we obtain a governing equation in discrete space that looks a lot like the Laplacian, and it is. And now the diffusion limit in this case is just very simply characteristic timescale goes to 0 as delta x goes to 0. This is a one-parameter family limit, and so it exists. It doesn't blow up. It also doesn't go to 0, and it yields the fractional diffusion equation. Now what we're going to do is we're going to say, okay, well, let mu depend on x. Now can we take the same limit? Okay, so from previously the discrete space governing equation then becomes now all the mu terms, the fractional exponent terms, become dependent on x. And the question now is, if now my denominator has a tau to the power of mu as a function of x, does that limit, the tau goes to 0, still hold for all positions of x? Okay. And I'm going to show you now that it doesn't, and actually we see a blow up. The best case that we can construct from this limit is that it's a valid limit, but unfortunately it's not a very physical limit. So let's suppose that we pin some value x star as the argument that minimizes mu x, okay? And let's say that we define a constant such that as tau goes to 0 and as delta x goes to 0, at this position x star, d mu at x star is a constant. If then we consider every position outside of that minimum, and actually this x star could be a set of points, if we consider all other x's that are not at the minima that don't give you the minimum value of mu, then what you'll see is that I can actually reorganize the original limit equation into a limit as tau goes to 0 of the pinned diffusion coefficient at the minimum value times 1 over tau mu x minus mu at the minimum, okay? And since mu at the minimum is less than mu everywhere except x star, you have a positive power multiplying tau, and it's in the limit as tau goes to 0, and therefore this diffusion coefficient blows up at every other position where mu is not a minima. And so this is not valid. The equation doesn't exist. The diffusion limit doesn't exist. If we now then say, well, let's go the other way. Let's pin x star to be where the fractional exponent is a maximum, then what you have is that the diffusion coefficient goes to 0 for every other point other than x being the maxima of mu's. And it's exactly the same reasoning. It's just that this 1 over tau to the power of the difference of exponents will be now negative. And so as tau goes to 0, you have the pinned diffusion coefficient at the maximum values times tau to the power of some positive value. Okay. While that's valid, and you might say, well, that's a perfectly valid equation, it completely destroys the reason why we wanted to model any kind of diffusion or fractional diffusion in the first place. So it basically means that nothing moves, okay? And so this is not a good situation. We cannot just naively take our equation from the constant order case and just apply the same derivation to obtain a diffusion limit to a partial differential equation that is the space-dependent variable order time-fractional diffusion equation. So the proposed fix to this is to actually introduce a new, another timescale. So if this is your old waiting time, the naive version of your waiting time, then we actually introduce another timescale called T0 that will rescale my my global time, so T. You basically rescale T with T0, and you also have an extra factor of tau outside. And this was introduced by Peter Straka in 2018 in terms of a continuous time random walk as a formal stochastic process and the formal limit. And tau is now something that you see as a dimensionless scaling factor, and T0 is now the characteristic time scale. And then if you do that, we can now define a diffusion coefficient in terms of delta x and tau, this dimensionless scaling factor, and now we're back to the safe land of our diffusion coefficient doesn't blow up, it also doesn't go to 0. Now the question is, what does this t naught and tau actually mean? And so from a continuous time random walk point of view, it's simply a trick to get your equation to exist again and for the diffusion coefficient to not blow up. It's a rescaling of sorts. And what I'm showing you here is a continuous time random walk governing equation. So you have, your transition in space, multiplying all of your kernels of your time or residence time dependent weighting at positions y, and then you have everything leaving your state x. And that translates, if we use this new waiting time with tau and t naught scaling, it translates to a very similar equation where we can now take the limit. The discrete time random walk governing equation doesn't have this luxury of introducing new timescales because inherently our timescales are stepping, well, it's fixed to 1 because we're in discrete time. And so we cannot play the same tricks. And so then the question becomes, how can we find the equivalent discrete time random walk governing equation for the variable order fractional diffusion? And it turns out the only other choice that we have, because we can't really modify the kernel, is to modify the transition rates in space. So transitions between lattice positions. So what we're going to do is, instead of assuming that all my jumps jump left and right with probability at half and there's nothing left in my original site, I'm now going to introduce a rest that is space dependent. So this is what you see in Rj. So Rj is the probability of my particles jumping out. So the time that the particle is waiting at site j has expired, and the particle is now jumping out, and the transitions after you've jumped out of that state, you could go to I plus 1, I minus 1, or you can actually go back to I with probability Rj, and it's site dependent. That's the change we're going to make. So here, psi is actually the waiting time, which is the discrete analog of your Mittag-Leffler function in continuous time. This is what we call a Shibuya distribution. And if we substitute these into my discrete time random walk governing equation, which is what you see in the equation following, then we obtain this expression, which is the equation at the bottom. So you can kind of see that this sum between 0 and to n minus 1 is actually a discrete analog of the integral kernel that we saw previously. And from this equation, we can actually embed the discrete time random walk into continuous time by defining that I is actually I delta x and n is delta t, and then using discrete analogs of Laplace transforms called Z transforms, we can also then obtain the fractional diffusion equation of variable order that we had before in the limit as delta x goes to 0 and delta t goes to 0 with a very well-defined diffusion coefficient that is now not just about introducing a random rescaling with no physical meaning, but now we understand what that meaning is, and it's the probability with which you return to your original site. And this also introduces more restrictions on what Rx could be and how that correlates with how you match that with calibrating that with your continuous time random walk. This has all been published, this has all been released in an archive preprint that we uploaded last year. It's currently under review. It's in Royal Society Journal. And so you can have a look about all the technical details there. And now next, what I'm going to move on to is I'm going to now say, before I move on to the next topic, what this actually gives us, this discrete time random walk formalism, it actually gives us a nice numerical algorithm to evaluate our, or to approximate our density. So just to remind you, so this is the discrete time random walk diffusion coefficient definition. So 1 minus Rx being the time that I wait at Rx, and delta t and delta x being constant. And then in the CTRW, we have some characteristic timescale t naught and tau being a dimensionless scale factor. And if we now equate 1 minus Rx with delta t to the power of mu x divided by tau times t naught to the power of mu x, then we can make the discrete time random walk equivalent to the continuous time random walk, and we have a very well-defined diffusion limit. And so what we now can see is that this dimensionless scaling factor was actually a control for the amount of self-jump probability at different positions. So it's actually the amount of loops that you make coming back. Okay. And in fact, yeah, so I should just mention quickly, I'm working with my collaborator at UNSW, William McLean, Associate Professor William McLean, to generate better numerical approximation algorithms. And this has been a really interesting topic to pursue. So as I said before, the discrete time random walk also yields a very useful first-order discretized numerical scheme. The good thing about this numerical scheme is that it conserves probability mass. So it's built into the numerical algorithm that if you sum up all of the masses, no matter how big your bin size is, they will always sum to 1. And so here what you're seeing in kind of the lines and the markers is your discrete time random walk numerical approximation. What you're seeing with the dashed lines that look like bars, that's actually a Monte Carlo simulation of the underlying stochastic process. And you can see through time, it actually matches up very well. And my fractional exponent has a minimum at x equals 0. And everything started at x equals 0.5. Now, what you see is that in the long time behavior, all of my particles start aggregating towards the position with mu being a minimum. Okay, so the fractional exponent where it's a minimum, in other words, where the trapping is the strongest, my particles tend to accumulate. And we also have, for those of you more physically inclined, it's a breakdown of your typical Boltzmann distribution, because what you'd expect in a diffusion equation with no potential, you'd expect uniform distribution, and yet now we start seeing a gradient of particles because the trapping strengths are different in positions of x. So the next question then becomes, can we find a solution? And it turns out the answer is yes, to some extent. The first thing I'm going to take you through is, can we find a solution for reflecting boundary conditions? And the answer is yes, but only asymptotically. So this is the asymptotic solution that my PhD supervisor, Sergei Fedotov, and I found during my PhD for a linear monotonically increasing function of mu x with some minima at x equals 0 and reflecting boundary conditions, of course. The way that you see this is that you start from the continuity equation and you say, okay, well, I can define my flux to be this object, the first derivative in space of my diffusion coefficient with my Riemann-Liouville fractional derivative of my probability density. And then explicitly calculating this, what I end up with is this horrible kind of 4-term expression. And what you'll see is that actually there's this third term where my mouse is right now involves a modified integral kernel quasi-fractional derivative-esque operator, but now you've got a logarithm of time multiplying your typical Riemann-Liouville fractional derivative. Okay, and this is going to make all the difference. In Laplace space, we can do the same thing, but what you're going to see is now the Riemann-Liouville fractional derivative actually simplifies to just having s to the power of minus mu, where mu is a function of x, and explicitly expanding this derivative, you end up with the gradient of your density in Laplace space minus that logarithmic term multiplied by the gradient of your actual fractional exponent in space. And so this term dominates as s goes to 0, because as you can see, my gradient in probability density, there's no s dependence at all. So to find this asymptotic solution, we essentially equate this equation to 0, and what we obtain is this partial differential equation in x, first order, and the solution to this equation is essentially s of the density is equal to t naught s to the power of mu x, and this denominator term here, integrating across all space, is just the normalization because it's a probability density. Now, since mu x is a monotonically increasing function and has a minima at x equals 0, as s goes to 0, so as the peak of my power law s to the power of mu x is concentrated in the neighborhood of x equals 0, we can use the Laplace method to approximate the integral in the denominator of the solution to obtain this expression, and substituting this back in and then inverting the Laplace transforms using these properties, which you can actually just look up at Grachtin and Rizik, or calculate yourself directly. You can arrive back at the asymptotic solution. Now, with this calculation, what we should take note of, which is what I mentioned before, is this asymptotic solution also has a very slow dependence on time with the introduction of this logarithmic factor that you see inside the square brackets. If we now look back at the flux, this logarithmic term is actually caused by the third term. There's this new term with a modified integral differential equation, integral differential operator that's very similar to a fractional derivative. It's just got this logarithm term at the top. And what this does is this is the term that causes your anomalous drift. Because if you can remember, just going back, this term that you see in red is actually dependent on the gradient of your fractional exponent. Okay, so it's almost like that gradient is causing a drift. And so that's exactly what you see. So this black dashed line is your asymptotic density. So it's an asymptotic solution. The bars show you the results from Monte Carlo simulations. And hopefully you'll agree that this does look as if the asymptotic solutions, at least in long time, match what the Monte Carlo simulations show us. The inset in this figure is basically just showing you that, yes, at x equals 0, that the growth of the number of particles arriving at this position is essentially logarithmic. Okay. It turns out, interestingly enough, that even if I introduce an advection into this equation, so let's say I don't just have my typical variable order fractional diffusion, but I also now have fractional diffusion advection at variable order, it still is incapable of negating that effect in the long run of my anomalous aggregations, this ultra slow anomalous aggregation that's dependent on this logarithmic term. And this can be seen, so in each of these two cases, the variable order fractional diffusion equation and the variable order fractional Fokker-Planck equation, you can see that once I've added this velocity, even though the velocity can be pushing you away from that trapping, the minimum trap, in the long run, as s goes to 0, this Vx term dependence will disappear for the exact same reason that it disappeared in the variable order fractional diffusion equation, because there's no s dependence. And what you see here is exactly that. So in this case, the inset is actually the solution if we were in the constant order case with the drift that's pushing you towards x equals a half. And the solution that you see in the main figure is actually what you obtain if you have a fractional exponent that's dependent on x. So hopefully now I've shown you that both analytically and with simulations and heuristically with images, that this anomalous aggregation phenomena is incredibly strong. So there's almost no way of getting around it, even if you add a drift. Okay. In the Laplace space, it turns out that we can obtain an exact solution, not just an asymptotic solution. And this can be done by taking the Laplace transform of the equation and solving, at least for the linear case, it turns out that it's a collection of modified Bessel functions, or the summation of modified Bessel functions of the first and second kind, at least with reflecting boundaries. And the particular solution is also Bessel functions depending on your initial condition. If it's a delta function, if it's a uniform initial condition, then you end up with Meyer-G functions. So Roth and Sokolov introduced this in Physical Review E in 2020, a year after our asymptotic solution, where they introduced this kind of special variable transform using these parameters, so zeta, omega, and epsilon. And as you can see, the particular solution for a uniform condition is the Meyer-G function like this, in this form. And so I had a very talented student join me at UNSW, Wan Cheng. He actually showed that in the limit, as s goes to 0, these expansions actually lead us back to the asymptotic solution that Sergey and I had published a year previously. And interestingly enough, the identities that we needed came from quantum field theory. So there was a quantum field theory textbook that actually already contained these asymptotic expansions for the Meiji functions. So now we move on to obtaining actual experimental evidence, because the whole point of this, remember back to formulating our modeling equation, ensuring that the diffusion coefficient exists and ensuring and finding solutions to the problem, was to see if we could model how distributions of organelles or distributions change when our fractional exponent becomes space dependent. So this is me sitting in a lab during my PhD. And if, as everyone knows, as soon as you move to experimental work, which is what you see here on the right, although it's very beautiful, so these are cells and the little red dots are the lysosomes that you're seeing, with green being the microtubules, essential for active transport. As everybody knows, when you move to real life, you end up with real life problems. And so what you end up with is you can actually measure how much of my particle distribution is located along a normalized distance, radial distance along my cell. And so what we measured here in black with the error bars is actually that exact probability density. So how much of that is located, of course, binned along a normalized distance away from the center of the cell. And we did a massive Monte Carlo simulation to then brute force fit this experimental observation to what we might see for our variable order fractional diffusion equation, if it is indeed the model that is suitable for characterizing this scientific phenomena. And of course, once we did that, we then did some single particle tracking experiments to see if where you were located in the cell actually determined your anomalous exponent statistics by measuring the mean square displacement of tracked trajectories. And this was published in Philosophical Transactions of the Royal Society A, 2021. So we found an asymptotic solution, and then what we did was we experimentally tried to see if our experimental evidence would be consistent with our model. And to a large extent it was, although there are still problems. Unfortunately, just fitting a density, or trying to estimate the anomalous exponent through mean square displacement power law fitting doesn't actually give you a unique characterization of the process. So you can only say that the model describes the process. You can't really say anything about the underlying stochastic process that these cells or these intracellular vesicles are actually moving with. And so we went to look at, well, how would you measure or detect that mu of x was changing over space? And when you think about it, if you look at single particle tracking experiments, it's inherently flawed, because as soon as you require multiple data points in time, you can no longer identify an anomalous exponent or a fractional exponent localized to a space. You have to make an approximation of a kind of an area where that anomalous exponent or fractional exponent is constant. Okay. So then the next question was, can we use mean square displacements? And there's this great paper by Sipatov, the first author, that explored what happens to mean square displacements if I have alpha of arbitrarily complex functions, as you're seeing here in green. The next thought that I had was then, can we use first passage times? Can we use first passage times to somehow differentiate? In fact, it's just interesting to say, what is the first passage time if we had a variable order fractional diffusion? Because everything gets trapped, and we shouldn't obtain the same first passage time statistics. So the first passage time that can be defined, the easiest way to find it is to find the survival probability in a domain. So this is psi FBT is the probability that my time of first passage is greater than some value t, little t, sorry. And that's basically just the integral of your probability density over your entire domain, so 0 to L. And our probability density is governed now by my variable order fractional diffusion equation, which you see here. on the domain, on the interval 0 to L, but now I modify my boundary conditions such that I have an absorbing boundary at x equals 0 and a reflecting boundary at x equals L. And just for ease of notation, we are going to use the initial condition delta function beginning somewhere at x0, where x0 is the value between 0 and L. So again, we take the Laplace transform, and if we define this term inside my second derivative of space, my Laplacian, as f, then we can actually put my variable order fractional diffusion equation in Laplace space into something that's more manageable in terms of f. And so I obtain this second order ordinary differential equation. It's not completely ordinary differential equation, but derivatives only in one variable. And since I can show, well, since in the long time limit I want s mu x divided by this diffusion coefficient to go to 0, and this occurs uniformly as I take my limit as s goes to 0. And also since I can show that this function fxs, which is the first term multiplied by a probability density, is bounded because of the property of it being a probability density, then what I can say is that this differential equation reduces down in the limit as s goes to 0 as a much more simple equation I can solve, and the solution in Laplace space is that f of x at s equals 0, so in the infinite time limit, in long time limit, is the minimum between x and x0. Okay, now I can basically substitute this result back into my equation for first passage time survival, and in Laplace space I can express this as this quantity here. So I still have that s to the power of mu x minus 1 inside the integral, but now my term inside f is now much more manageable. It's just the minima between x and x0. Okay. And so for a whole bunch of different cases, so when there's a unique interior minimum, in other words, the second derivative in space of my fractional exponent is a constant. For multiple interior minima, so when there's functions oscillatory and there's multiple minima, higher order minima, so quartic minima, and higher, absorbing boundary minimum, so a minimum located at x equals 0 versus a reflecting boundary minimum, obtained at x equals L, I can obtain my Laplace transformed approximations, again, using the Laplace method of my first passage time survival functions. And these are what you have. And now what I want to point out is that, interestingly enough, I now see, again, the appearance of these logarithmic terms in time, rescaling my power law time distribution that I would expect from a constant order case. And so if I then go to the next, we basically use, to convert from Laplace space to real time, we can use Tauberian theorems, in this case, the Karamata Tauberian theorem specifically, and basically, we define this slowly varying function as lambda x on Lx goes to 1 as x goes to infinity. And we can define that as my log t0 s minus nu. And this nu is actually an order parameter that is determined by the geometry of where my minima is. So if I go back, you'll see that in this case, nu would be a half. Right? So when there's a unique interior minima or multiple interior minima, nu here in the higher order minima is 1 on k, where k is the order of the minimum that you have, and k is always even. The absorbing boundary minimum, nu is 2, and the reflecting boundary minimum, nu is 1. Okay. And so if I now convert all of these into real time, you now see I have a logarithmic dependence on time in the denominator, and I have a power law dependence on the minimum value of my anomalous exponent for my first passage time survival times. And this is an asymptotic relation. Now, at the bottom here, you'll see that for my constant order case, so if mu x did not change at all, the first passage time survival function would scale as t to the power of minus mu. And so you can immediately see that by introducing my variable order component, so as my fractional exponent varies over space, I end up with actually t to the power of minus mu, but now mu is the minimum value of my fractional exponent in the entire domain. And also depending on the geometry, so if it's located at different positions, I end up with different corrections with logarithms of time. And so this provides a very, very powerful tool now, because we can now then go into experiments and probe whether what we see is variable order fractional diffusion. So if something is known to be fractionally diffusive, we can now go and measure first passage times from that experimental system, now that we have all these relations, and figure out whether the geometry of alpha, first of all, is space dependent. Sorry, not the geometry, whether the value of my anomalous exponent or fractional exponent is space dependent, and also whether the geometry of that function is a specific case. So whether it's, the minimum's located somewhere, or it's a functional form, higher order, something like this, polynomial. So just to show you for the linear case, so when my fractional exponent is linear, I have here plotted Monte Carlo simulations, numerical inverse Laplace transforms by the Gavin-Steffes algorithm. This was basically the numerical Laplace inverse Laplace transform of those exact Laplace space solutions that we found thanks to Roth and Sokolov in the previous slides. And of course, that dashed line that you're seeing is the Tauberian tail that our theory predicts. And all of these are first passage time survival functions. And what you're seeing on the left versus the right is whether you have a minimum located at 0, so the gradient is positive for mu, or the gradient is negative for mu, and the minimum is now located at the reflecting boundary. And hopefully what you can see is that the tails, at least for when my minima is located at x equals 0, is much more steep. So you have almost a finite first passage time, mean first passage time, compared to when I have the minimum trap located at my reflecting boundary. And this is intuitive, because if your minimum is located at your absorbing boundary, everything tends to aggregate there. Whereas if your minimum is located at the reflecting boundary, everything aggregates towards the reflecting boundary, and nothing gets past that first passage problem, going past x equals 0. We can also do this for arbitrarily complex functions, and we can actually test whether our Tauberian tail matches the theory. And so what you're seeing here is a Monte Carlo simulation of my first passage process, and then this red line is the Tauberian tail that our theory predicts. And what you're seeing in the inset is actually what is the function of my anomalous, my fractional exponent, and then what's the distribution of particles that I see in long time. And this work has also been uploaded onto arXiv very recently. It's currently under review in Physical Review Journal. And the most exciting part of this is that we can now begin probing what is the shape of my fractional exponent in real experimental systems. And these are distinguishable by measuring my first passage time statistic tails. And so we're currently working on, how to obtain statistics. So how much data do we need in order to be able to differentiate between different powers of logarithms, and also a more general theory on what if I end up with the order parameter nu, which tells me what shape my alpha is, that doesn't fit any one of those 1, 2, or 1 on k cases that you saw, or square root half, right? Okay, so with that, I'd like to conclude my talk with some acknowledgements. So obviously in the University of Manchester, I've been working with my PhD supervisor, Sergey, with long-term research associate, Nikolai Korabel, who's now moved on for a permanent position at the University of Hertfordshire. Vicky Allen, Mark Johnston, and Thomas Way were my experimental collaborators who helped me do everything in the lab. We also had a talented team at UNSW working on this, led by Bruce Henry. And then in the group, we had Chris Angstman, Boris, who's my PhD student, joined with Chris, and then Zhuang, who was a postdoc of Chris, who's now working at Cambridge, and my current master student, Wancheng Li. And obviously all of these people contributed a lot. And I'm looking forward to very exciting projects with APROF Bill McLean, also at the University of New South Wales working on numerical algorithms, but that work wasn't presented yet. It's just a bit too early for that. And I'd just like to thank all of these institutions that also funded this work and funded me, I guess, going through this process. So thanks very much for listening to my talk.
Thanks, Daniel, for the very nice talk. It was quite exciting. For questions, please raise your hands. I'll call out your name in the order they appear on my screen. You could equally unmute your mic and ask a question. I have some curiosity, if I may take this opportunity. So it was very nice. It was very nice to see that for the time operator you had a space dependent space dependent fractional order, and this is nothing. This is something which is very hard to imagine. So happy to learn about it from you. So
This one.
yes. So yes, yes.
Okay.
Uh, uh, so I was, because what I would normally imagine, like, because space and time, you can treat it differently, and they can have their orders differently, and so anisotropy can be in each dimension. Time does not have to follow the same dynamics as space.
Yes.
So each dimension time is just one dimension, but you show that that it's actually dependent on space. It's coupled with space, the order.
Yes. So so if you think about the underlying stochastic process, it becomes, in my opinion, a lot more clear. So if I go back to when I introduced these diagrams here, so generalizing from the diffusion equation to the fractional diffusion equation, we just said that the rate at which I jump from site X now depends on how long I resided in site X, and that gives me lambda tau. And that's actually what generates me the Riemann-Liouville fractional derivative in my governing equation, right? The underlying mechanism. Now, if I say that, well, the rate at which I jump out of a state also now depends on my state itself, so where I am. In other words, every single position on that line now has a different waiting time of how I move. Then you end up with the variable order case. Now, I agree with you. I have no idea what the more general variable order problem is in terms of what if this thing was also dependent on time itself, right? If it's a non-stationary like that, I still don't have a good handle on what that is. But if it's just dependent on space and not system time, not global time, then hopefully what I've shown you in this talk with the global diffusion limit and reformulating it as discrete time random walk, it's then possible. So basically, it's the concept that every time I jump, it depends where I am, the rate at which I jump, and on how long I've been there. And as I take that to the continuum limit, so as my distance between each neighboring site goes to 0, I'm able to reconcile a global diffusion limit by introducing in the transitions a jump back to my original state. That, yeah.
Yeah, okay. Okay. I think I put this. Okay. I think I understand your case, but think about this. Think about this. So, in space, you're making a longer jump, but in time, you can just you do not have to make a longer or a shorter jump, and 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 with this description you can actually decouple space and time, and then you're doing super diffusion in one space, and then you're doing subdiffusion in time, but given that mean square displacement equal to that tau to the power something, not sure how to actually fit this description into that part. So this is how I would actually understand it, because the random waiting time and the space jump uh, can be two independent of each other, but jointly put together gives you the whole dynamics. So that's what I was actually very surprised to see. Uh, 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 a very different approach. I think I'll need some time to actually comprehend it myself.
Yeah, I mean, it's I can tell you right now, I'm
Yeah,
working in this field and I still need to understand. I still don't understand a lot physically and intuitively about this system. So
yeah, exactly. It takes time to build the intuition. I
yeah.
see Bill has a question. Bill, please go ahead.
Yeah, I guess there's no particular barrier to doing this in 2D or 3D.
Exactly, yeah. There's absolutely no barrier to doing 2D and 3D. And actually, in this paper, in this preprint that we have released, there in the appendix, we've actually derived higher dimensions with the proper limit. Yeah, so definitely there's no difference in doing 2D and 3D. And actually, it would be incredibly interesting to figure out how do the first passage times change as we move to higher dimensions and different geometries.
Okay,
Yeah, thanks very
Yeah,
much for that.
that's all.
Yeah, thanks very much for that question.
Do we have more questions? You can either raise your hands or unmute your mic. Possibly no. So I think I'll possibly point you out in the direction of hyperdiffusion and ballistic, because that's where you put a question mark. So
Yes.
we had this talk in 2024 by Federico Naspoli. During that time, he was at Princeton Plasma Lab. I'm not sure where is he now. Possibly still there, but the recording of that talk failed, which is rather unfortunate. But I'll send it to you nonetheless, for the paper. So what they are trying to do is like you have a plasma within a tokamak. So they are
Oh,
studying fusion. So they are studying
yep,
fusion,
yep.
complicated stuff. And they have a plasma turbulence that they talk about, and one way to talk about talk about it is using a fluid equation. So it describes turbulence, and in their computational experiments they put some little dust into it and try to see the trajectory, and that's the point they started talking about ballistic and hyperdiffusion motion. I can
I
send
see.
it to you. I can send that paper to you, and the link to the talk.
That'll be
Oh
very
no,
interesting.
the talk failed. The recording failed, which was rather unfortunate. We had a technical issue that day, but but it was very interesting to actually see, at least in the computational exercise, to get a handle on what's going on hyperdiffusion.
Yeah,
It was very interesting.
definitely.
Uh,
Thanks.
Are there any more questions or comments? You may please unmute your mic. Do you have anything more to say, Daniel?
No, I think thanks very much for having me. It's been a pleasure to present. And yeah, I'm looking forward to the other talks.
Yes. All right, then this is a good point to stop here and close this talk here. Thanks again, Daniel, for the very nice presentation and for the engaging discussions. All right, guys, then we'll see you next week.
All right. Bye.
Yeah.